So we've seen this sort of bonding diagram before, that over here we have atoms very far apart, and they get closer and closer and closer, and they eventually make a bond, get too close, and those nuclei repel each other. But what are the electrons doing as these things get closer and closer and closer? They're changing shape. So over here we have atomic orbitals. And we've talked about atomic orbitals before. We've talked about S, P, D, F, G, H, I. Yeah, we've talked about those types of orbitals. We said an S is a sphere, and a P is a dumbbell, and a D, I'm not even going to try to freehand over here, but we've seen those. Atomic orbitals have very specific shapes. As you come together and make bonds, this molecule that's making a bond no longer has a spherical shape or a dumbbell shape. They reform into newly shaped organization of electrons, let's say it that way. What the heck do I mean? Why does this matter? Well, we just finished talking about how something that has 3 atoms around a central atom will have a 120-degree bond angle. So BF3, we know, we have measured in the lab a bond angle of 120 degrees around the boron, the central boron. The SBF bond angle is 120. So if we go back to what we know about boron and its atomic electron configuration, there we go, we would say it's a 1s2, 2s2, 2p1. So these are the spots available for making a bond to boron. The p orbitals are what's available for making bonds. So if I have a p orbital this direction and a p orbital that direction, those are 90 degrees from each other. So remember, we have one along the x-axis, one along the y-axis, and one along the z-axis. Those are all 90 degrees from each other. P orbitals are always that way. So if F comes in and tries to make a bond from a p orbital in F, making a p orbital bond to boron, and a p orbital in F, making a p orbital bond to boron, that would give me a bond angle of 90 degrees. That's not what actually happens in BF3. So we need to come up with some way to describe how do we actually observe a bond angle of 120. It must be because these atomic orbitals are not being used to make bonds. We're going to use hybrid orbitals to make bonds. What are hybrid orbitals? That's what I'm here to tell you about. We're going to use hybrid orbitals to make bonds, but when you have a neutral free-floating atom, we will talk about atomic orbitals. So if we continue our discussion of BF3, this down here at the bottom is the s orbital, 2s, that has 2 electrons in it, and the 3p orbitals all around the central axis that has 1 electron in it. That's our 2s2, 2p1 setup here. These are atomic orbitals. Okay. So boron needs to make 3 bonds. So in this hybrid orbital thing, when you need to make 3 bonds, you need to take 3 atomic orbitals and mathematically average them to get 3 hybrid orbitals. If you take 3 atomics, you get 3 hybrids. You take 2 atomics, you get 2 hybrids. Take 4 atomics, you get 4 hybrids. Got that? So if we need to make 3 hybrids, we need to take 3 atomic orbitals, mathematically average them. So if we average a low energy and 2 higher energies, we're going to get 3 hybrid orbitals that are lower energy than the 2p, but higher energy than the 2s. It's the mathematical average. If we had drew an energy scale over here, would help if it's straight, but it's not. These hybrid orbitals are between the energies of the 2p and the 2s. Okay, so I got 3 hybrid orbitals. I have 3 electrons to distribute through those hybrid orbitals. 1, 2, 3 electrons to distribute. I'm going to call these hybrid orbitals sp2. The reason I name these sp2 is, what did you take to average together? You took 1 s and 2 p's to average together to make these things. So sp2 hybrid orbitals are always a combination of 1 s and 2 p's. So now I've got these 3 electrons distributed. I can make 3 new bonds. That's where my BF3 comes in. We know an s orbital is a sphere. We know a p orbital is a dumbbell. And sp2 has characteristics of both a sphere and a dumbbell. What? Yeah. It's kind of dumbbell shaped, but it has a small side, a small lobe, and it has a larger lobe. That's what happens when you mathematically average in a sphere and 2 dumbbells. Yep, we're averaging those pictures. Isn't that the craziest thought ever? There's my 3 little electrons in that stuff. There's my 3 little bonds. When we make a bond using a hybrid orbital, we're going to call that thing a sigma bond. So boron makes 3 single bonds using hybrid orbitals. We're going to call those single bonds sigma bonds. Okay? What about something like beryllium BeCl2? Beryllium needs to make 2 bonds to chlorine. That's an E. So 2 bonds means I need 2 orbitals to make 2 bonds. So combine 2 orbitals. 1 s and 1 p are combined together. My hybrid orbitals are going to be energetically in the middle, right? Because it's one of these and one of those on the energy scale. In the middle, there's a 2s down here. Halfway in between are the 2 hybrids. And then I'm going to call these sp. Why might I call them sp? Because I took 1 s and 1 p to average together to make these new hybrid orbitals. Okay, my 2 electrons, there they are, 1, 2. What do sp orbitals look like? They look kind of like a dumbbell, but kind of like sp2 orbitals. There's a small side, a small lobe, and a big lobe. These have a little more spherical character than the last ones. So if I'm hand drawing it, this might be an sp, while this one that's a little bit longer and leaner might be an sp2 because it's got more p character. And this one that's even a little bit longer and leaner is an sp3 kind of orbital. There, this one is a little more sphere-like because it has a little more sphere-s character. Yeah, okay. These are pink sp2 orbitals. They're making sigma bonds. Oh, that doesn't show up. This is a sigma bond. This is a sigma bond because I'm using a hybrid orbital to make those 2 bonds. Okay. NH3 is a little bit different from what I've been describing in that I need 4 hybrid orbitals. The reason I need 4 hybrid orbitals is that I need that lone pair to be held in a hybrid orbital. How do you know if you need a lone pair to be held in a hybrid orbital or not? Well, if you look at our last 2 examples, they didn't have any lone pairs. So we're going to always assume that a lone pair needs a hybrid orbital to reside in. So this thing has 3 bonds that it needs to make, but a 4th position that needs to be a hybrid orbital too because it's a lone pair. So 4 hybrid orbitals means you need to combine 4 atomic orbitals to get there. So I'm going to combine all 4 of these. And what might you call these hybrid orbitals? sp1, p2, p3. sp3 hybrid orbitals. You'll note that they're quite a bit higher in energy than the 2s orbital is. That's because there are 3 p's to bring that average up closer to the p's. Nitrogen has 1, 2, 3, 4, 5 electrons around it. Those 2 are the 2 that pair up as my lone pairs. That's why there are 3 vacancies for bonds. Vacancy, vacancy, vacancy. We can make 3 bonds around this nitrogen because I've got a place to plug in 3 new electrons. I've already kind of told you what sp3 orbitals look like. They look like this. A little tiny lobe on one side, a bigger lobe on the other. They are around a central axis that has a 109.5 degree bond angle when you tie all 4 of these orbitals together in the middle, right? Right. This is a sigma bond. This is a sigma bond. This is a sigma bond. Yep. This, using sp3 hybridized orbitals tells me that it should be a 109.5-ish degree bond angle, a little bit smaller because of that lone pair. Water is also tetrahedral. Water has 4 things around that central oxygen. So water is sp3 hybridized. Yep. Sigma bonds in water. Okay, do molecules really use these hybrid orbitals? Well, we don't know. It's our current working theory. It's a useful model for describing why bond angles are what bond angles are. We observe bond angles in experiment. We have to reason through why they might be that way. And hybrid theory is reasoning through why our bond angles might be that way. So when you're assigned the task to assign the hybridization, predict the hybridization of a central atom or even a non-central atom, how do you do that? Count the number of lone pairs and the number of atoms bonded to the central atom, and that will tell you hybridization. If you have 2 bonded atoms, it's going to mean you need 2 hybrid orbitals. So combining 2 hybrid orbitals, we're going to call it sp, 2 hybrid orbitals. Anytime you have something sp hybridized, that means you're wanting to make 2 bonds around a central atom. That means they're far apart in space as they can possibly be, 180 bond angle. Anytime you have 3 bonded atoms, it's going to mean you need 3 hybrid orbitals. 3 hybrid orbitals means sp1, p2, sp2. Anytime there are 3 things around a central atom, that's 120 degrees. 4 means sp1, p2, p3, sp3. That means 109.5. Did you notice that something with 2 we would call linear, and that like totally throws it back to the last video? Something with 3 we would call trigonal planar, and that throws it back to the last video. Something with 4 we would call tetrahedral. Last video, geometry stuff. Something with 5 we already know has a bond angle of 90 and 120. So where do we get that 5th orbital to hybridize? We've already used all of our p's. S, p1, p2, p3, that only gets us to 4. Bring in the d's. So sp3d, and our last one, sp3d2. Yep. It's really all about knowing the number of bonded atoms and lone pairs and being able to count how many hybrid orbitals you need. That's all. But before we move along, if we're talking about something that's sp2, this CO3 2- without all those colorful pictures around it, CO3 2- looks like this. It's carbonate. Carbonate has this kind of Lewis structure. We need to make 3 sigma bonds. Because there are 3 atoms around that central atom, 3 oxygens around that central carbon. So 3 sigma bonds means we need 3 hybrid orbitals. So that's where we get that this is sp2 hybridized. What happens to the unhybridized p orbital? So we used up 2 of the p's and the s, but there's still a p orbital that is unhybridized. What is it used for? It's used to make a pi bond. What? All single bonds are called sigma bonds, and all double bonds consist of 1 sigma and 1 pi. And the way that pi is actually made is through using the unhybridized p orbital. Let's see what that looks like in pictures that textbooks have so that I don't have to try to draw it for you. It's used to create the second bond of your double bond. So here's my green hybrid orbitals, and in gray on that same image is my unhybridized p orbital. My green are all 120 from each other, and the gray is 90 degrees from those others. There's my hybrids. This gray is my p orbital. It's going to come up eventually. All double bonds are 1 sigma and 1 pi. Yeah. Because I'm having to use the p orbital, it's the p orbital that's in a different plane. It's orthogonal to, it's 90 degrees to the other things. The pi bond is electron density buildup above and below the plane of the molecule. So a sigma bond is electron overlap directly between two atoms. A pi bond is always electron density above and below the plane. The shapes of these pi bonds and sigma bonds are different. A pi bond is made from two p orbitals. When you're given a molecule like this, sometimes you'll be asked the question, how many sigma bonds, how many pi bonds? Well, all single bonds are sigma bonds, and one bond of each multiple bond is a sigma bond. So 1, 2, 3, 4, 5, I've highlighted them in red, and this pi is, this second bond of my double bond is a pi, and it's highlighted in blue. Bonds that are made from direct overlap between atoms are called sigma, and you use hybrid orbitals to make sigma bonds. You use unhybridized p orbitals to make pi bonds. Pi bonds have overlap above and below the plane of the molecule. So here's a combination of all the orbitals to see how bonding in ethylene actually looks. Sigma bond is direct overlap between the atoms. Pi is above and below the plane. This is not two pi bonds. One single pi bond has electron density above and below. Have I repeated myself enough? Maybe. Sigma bond directly between, pi bond above and below. This is only one pi bond. Okay. I don't know what else I want to say here. Oh, yeah. The pi bond prevents rotation, so single bonds can rotate. But because there's something tying this carbon to that carbon above and below, you can't spin this molecule around. You can't make this hydrogen go backwards while this hydrogen stays the same. Restricted rotation. It's a big deal. I'll tell you why in a moment. Let me talk about acetylene for a second first. Acetylene has a triple bond in the middle. Triple bonds, all multiple bonds have one sigma, and a double would have one pi, but a triple has two pi. If one pi is good, two pi is better. One sigma, two pi in a triple bond. So this is overlap in the middle. This is showing my hybrid orbitals coming together to make my sigma bond. This one set of p orbitals, the pz's, are making one of my pi bonds, and the py's are making my other pi bond. So two yellow hot dog buns, are one pi bond, while the other two yellows are the second pi bond. There are two pi bonds. You have two hybrid orbitals, two unhybridized p orbitals. Oh, yeah. All single bonds are sigma bonds. One bond of each multiple bond is a sigma bond. The rest are pi bonds. Yep. I'm going to take you a little bit deeper for one hot second. You can talk about something having pi character. It doesn't have all the indicators of being a pi bond, but it has pi character. What? Here's a giant molecule. It's an organic giant molecule. You can say this is a double bond oxygen, this is a single bond oxygen, or you can draw the resonance form where this is a double bond oxygen, this is a single bond oxygen. Yeah, what difference does it make? Well, if this is a single bond and solely a single bond, rotation can happen around this atom. But in reality, this bond has some pi character. And it has pi character to make this bond not rotatable. This hydrogen cannot free float, swing around, cannot rotate. What does that matter? In organic chemistry, you will talk about why pi character in a bond like that matters. I'm going to leave that a little bit vague for now to say in cell biology and in biochemistry, you will learn how why pi character matters. Proteins and peptides are combinations of amino acids. And when amino acids get together, they make these things called peptide bonds. Peptide bonds all have pi character. And when something has pi character, it means it cannot rotate. No rotation around something that has a pi character. So if our peptides could rotate, our proteins and DNA itself actually would have a different shape. But because there's pi character in all of our peptide bonds, proteins fold the way that they do, and they're able to behave physiologically the way that they do. Maybe that was a good enough teaser, maybe that just left you really confused, but sometimes it's really hard to know why all this chemistry stuff that you're learning relates to anything in the real world. This is one place where it's super obvious how this stuff relates. All right, that's good. I'm done. Goodbye.